In this lecture, we're going to talk about network initialization. In the beginning, before training, we need to set all the network parameters, all the network weights, to something. Since network training is some form of optimization, and we have some intuition about optimization, surely we can just set all the network parameters to 0 and begin optimizing. Unfortunately, that does not work. And in this lecture, we will look at several solutions that do work. We see a bit how these solutions are derived and show some practical examples. Let's start with some high-level observations about initialization. First, initialization of the weights is important. If the weights are not initialized appropriately, training can go horribly wrong. Second, initialization of weights is a heuristic, very similar to almost all other things in deep learning. One way to derive this heuristic is to derive equations using simplified assumptions. For example, using the assumption that the samples that will be fed into the network, the data, are random images. And these assumptions are only simplified, and therefore it's not like guaranteed that these heuristics will work, but it gives you at least some intuition why such a derived heuristic might be meaningful. Another way to do this, to derive a heuristic, is just create heuristics experimentally. You can take your data set that you're working on, or a well-known data set, and just feed it into the network, and then you observe what happens and try to fix the initialization heuristic until you seem to get good results. Next, we can observe that different layers, or maybe even different network types, use different initialization strategies. So even if you have one single network, it is common that each layer has a different initialization strategy. Then, in practice, what you're doing is often you just use the default values provided by PyTorch or TensorFlow or Keras, whatever library you use. In this course, PyTorch. These libraries have good and meaningful default values, and very often these default values will work well for you. Also, if you work on a particular problem, you want to look at current state-of-the-art models in your area and just check what they are doing. In addition, I really recommend starting by reading the PyTorch documentation or whatever other package you're using. Often you will see that if you look at online courses or you look at papers, you look at blog posts, that these might be slightly outdated, and that the PyTorch documentation might be more up to date with not maybe the very latest, but at least with the somewhat reasonably new initialization strategies. Here I would like to discuss 4 main factors that can be identified that influence what initialization is being used. Also, what I will be talking about here are variable names that I will use when I discuss solutions. A bit untypical maybe, I will discuss the solutions first after this slide, just tell you what the final result is, and then a bit later on how these solutions were derived. So let's discuss the four main factors. First, we'll consider a layer at a time, and so for one particular layer, we have this variable din that tells us the number of inputs. For a linear layer, the number of inputs would be the dimension of the input vector. For a conv layer, the number of inputs would be the filter width times the filter height times the number of input channels. So with number of inputs, you see what we call number of inputs is the number of inputs that influence one particular output value, not the total number of inputs. So that explains why in a conv layer the number of inputs are considered what they are described in this line. Then we have the number of outputs, d out. A third factor is the type of nonlinearity. For example, 10H, sigmoid, ReLU, leaky ReLU can be considered differently. Looking at PyTorch, the PyTorch documentation uses the concept of gain. And there are these gain factors that are different depending on the activation function, on the nonlinear activation function. So, for example, sigmoid has a gain of 1, 10H has a gain of 5/3, the ReLU has a gain of square root of 2, and the leaky ReLU has a gain of square root of 2 divided by 1 plus negative slope square. As a fourth factor, the type of network or maybe type of application is something to consider. Maybe type of network, do you use RNNs, transformers, GANs, variational autoencoders? So this is why I would recommend to look at recent state-of-the-art models in your area and check specifically what they are doing. Let's review again the three variable names that we will use in the next slides. din, the number of inputs to a layer, dout, the number of outputs, and gain, a factor that depends on what nonlinearity is being used. So here are some popular solutions. The first idea is to use uniform initialization. What we mean by that is we're going to sample each parameter of the network independently from a uniform distribution that goes from -a to +a. We can see that this interval of the uniform distribution is centered around 0. That seems very intuitive. Also, independently sampling just means that for each parameter in the network, we just sample it independent of any of the other parameters in the network. So really we sample one scalar at a time from this uniform distribution, then the next one, conceptually at least. In code, of course, we try to parallelize and sample everything at once as much as possible. But really, you think of, when you think of this sampling, you just think you have one parameter that samples from one uniform distribution, from this uniform distribution. And so how should we set A? So one solution is called Xavier uniform in PyTorch, and this suggests A should be set to gain. This is the factor we described before, depending on the nonlinearity used, times square root of 6 divided by d in plus d out. Number of inputs plus number of outputs of that particular layer. Let's just do a quick sanity check of what this equation does. So sampling uniform means that each value in the interval has the same chance of being picked. So if A is a larger number, then the interval will be larger. And in general, we would expect that, at least in terms of absolute value, there will be more larger numbers being sampled from. So when we want to initialize with very small values, then we would have A being very small, and when we want to initialize with larger values, then A would be a larger number. Let's see how that behaves, and let's just look at D in as one of the determining factors. So if D in is small, let's just say D in is only 1, and if D in is very large, let's say D in is 1,000, we just want to check when we have more inputs, does this value A get larger or smaller? So if D in is 1, or if it's 1,000, what is going to happen to the interval? So quickly thinking about this should reveal that if the number of inputs grows, then this value here will become smaller and smaller. So the more inputs, the smaller the weights that we will initialize this layer with. And this is a phenomenon that we will see kind of throughout also these other initializations that are suggested. So the same for the number of outputs. So what we can observe that in general, more inputs and more outputs let us initialize with smaller weights. There's Kaiming uniform in PyTorch, which recommends to, and there are two different versions. One is to set A to gain times square root of 3 divided by D in, or gain times square root of 3 divided by D out. D in, again, number of inputs, D out, number of outputs. And you see the same behavior. The larger D in or the larger D out, the smaller the value A, and then the smaller this uniform interval that this interval that you're sampling from. Another standard distribution is normal. The normal distribution, so normal initialization, we sample each parameter independently from a normal distribution with mean 0 and variance sigma square. In general, the mean that is recommended is 0. Of course, there are also versions where you might want to initialize with some mean value that is higher than 0. All right. Xavier normal initialization in PyTorch is sigma equals gain times square root of 2 divided by D in plus D out. Note that there's this relationship between standard deviation sigma and the variance that the normal distribution is parameterized by. As we know, the variance is the square of the standard deviation. And having sigma equals this term, then we have this, the variance, sigma square, is the square of this term. So this variance would make this square root go away. What we will see later, and I will highlight that again, is when we actually take the values from a regular normal distribution that has standard deviation and variance 1, and we want to multiply the values with something to make it into a normal distribution that has a variance sigma square, we multiply the values with sigma and not with sigma square. We'll see that in code later. Kaiming normal in PyTorch sets sigma either to gain divided by square root of d in or gain divided by square root of, this should say, d out. One version of this initialization, I call it the traditional normal initialization, sets sigma equals 2 square root of 2 divided by d in. This is what you can see derived in several lectures, blog posts as a standard normal initialization. There's also one initialization that, of course there are many more, but one that I mention here on the slides, where the values are not sampled independently from each other. The idea is if, let's say, the weights are a matrix, for example, for a fully connected neural network, then we would like to initialize the weights as an orthogonal matrix. The idea might be that the different rows of such a weight matrix are different filters, and by making these filters orthogonal, we ensure that they are not too similar to each other when we start training. There might be other ideas, so there's a paper you could go and look it up, how the authors argue for this initialization. There's one more thing that I would like to mention that's not on the slide right now. That is the idea of sampling from a truncated normal distribution. A normal distribution has no bound on how small or how large the values can be. That could create, and almost certainly will create, outliers. It might not be good to have these outliers, and a truncated normal distribution just says that if you sample a value that happens to be outside of the allowable range, which is a parameter you can set, then you will resample. So it's a normal distribution where outliers are not allowed. This is another version of sampling that people use. Some words about initialization of biases. Most of what we said before applies to the linear weights in the linear layer or the filters in a convolutional layer. The biases are typically initialized with 0. I believe this is the most common way to initialize them. An alternative argument could be made to initialize with a small positive value, maybe 0.01. And intuitively to argue that this lets the ReLU maybe a bit more likely stay on the positive side, and so you would get a better gradient signal since there is no gradient signal if the ReLU outputs 0. It is not really clear how well that works, and as far as I know, this is not a dominant or a common idea. Let's talk about one problem with the terminology. There are two well-known papers. One has as first author Xavier, and this leads to the name of Xavier or Clairaut initialization. Another well-known paper has a first author Kaiming, and this leads to the name Kaiming or He initialization. But there is a big problem, that is that the terminology is very inconsistent. These papers were generated a bit earlier, and the implementation somewhat evolved, but the names stayed the same. So people would take the original ideas and evolve them or generalize them. Say, well, this is Xavier initialization. Maybe it was derived for a 10H nonlinearity. Now we generalize it to other nonlinearities, or we make some other form of addition, or we make it more general by having this gain factor. So during this evolution, a lot of different initializations are called Xavier initialization. So if someone says that they're initializing using Xavier initialization, it is my conjecture that this doesn't really tell you that much, and that could mean a lot of different things. Same is true for Kaiming or He initialization. I therefore refer to the PyTorch documentation and use the names that PyTorch in the current version used, and that at least should be clear what is meant. Let's go back and start at the beginning. How did we derive these magical numbers that I just presented without any argument? They just came out of nowhere. Let's just identify a few potential problems. One problem is called symmetry. Different neurons, meaning different outputs of one layer, can be coupled together in a way that they are not able to learn different functions. We will show a bit of that or discuss that soon. Exploding gradients. Gradients in the network can become too large. Learning is unstable, and maybe the generation of floating point overflows results. Bad are also vanishing gradients. The gradients in the network could become too small, and learning is simply too slow. Let's discuss this symmetry problem. Now, we come from optimization, and zero initialization seems to be a great thing in many cases. We would argue that half the weights are expected to be positive, and half the weights would be maybe expected to be negative. And we don't know are they going to be positive or not, so guessing that they're kind of be distributed around zero makes sense. So as a best guess estimate, why not initialize everything to zero and then see how things evolve? And this leads to the symmetry problem. All neurons in a layer compute the same output. Now, this means we are considering let's say a fully connected layer. It is easiest to see why this is true. And then all neurons in the next layer receive the same values as input. And then all neurons will receive the same parameter updates during backpropagation. And this last point is what really kills it, because even though the weights might change during training, they all change the same way. So if we imagine a fully connected network layer, then we start with all weights being zero, and then after one update, maybe all weights are 0.1. And then maybe another update, then all of them could be something else. This is just looking at one layer kind of in isolation. All right, so we need to be a bit careful maybe with what exactly we are claiming here. So let's look at one example with two neurons. So this linear layer has two inputs, x1 and x2, and there are two neurons, neuron 1 that has the weights w1 and w2, and the second neuron that has the weights w3 and w4. So what does the local gradient, the local derivative of the weights depend on? That will depend on the data values, x1 and x2. So here we would then say that this local derivative might be the same for the two neurons, neuron 1 and neuron 2, in the sense that W1 is coupled to W3 and W2 is coupled to W4. Now, if the upstream gradient is different for neuron 1 and neuron 2, this would solve our problem. However, this is not the case if everything is initialized with 0. In addition, we can look at some later layer in the network. In some later layer, let's say all the weights were 0, all the values were 0, so then we might have such a layer that has all the w's and all the x's be 0. That means that then the gradients, the local gradients, will also be 0. So once the gradient is 0, then the gradient, since it's multiplicative, there's no more gradient signal to earlier layers in the network. We just have to be a bit careful because the gradient signal can come from all over the place. It's not only that there's a path that goes usually through the layers from the last layer backwards. There are also these, let's call them shortcuts. For example, the regularizer directly connects weights to the loss function, and there will be some direct feedback from the regularizer. For example, if the regularizer is a bit weird or has some way to treat different weights differently, this could lead to a breaking of the symmetry. Also, there could be other network layers that introduce some form of randomization. This might also lead to breaking of the symmetry. Still, for most simple and most practical networks you could think of, initializing the weights with 0 will not be able to break symmetry, and therefore a layer that might have 100 neurons, but all of the neurons being coupled together will act the same way as a layer that only has a single neuron. While zero initialization causes this additional problem that once everything's 0, the gradient is dead anyways, we also have to be cognizant of the fact that initializing the same way and having a symmetry leads to a symmetry problem that can also be there if one is not careful and one doesn't necessarily initialize with 0. So initializing everything with 0.01 will also not work. That leads to the next obvious idea, initializing the network with small random numbers. This will break the symmetry, undoubtedly. So let's just assume we have some rank n tensor of size r to the power of d1 times dn, where di is the dimension along axis I. Then we can look at the Python commands to initialize such a tensor with small random weights. Maybe it's a rank 2 tensor for a linear layer. If you want to have independent samples from n0, that is a normal distribution with 0 mean and variance 1, then we would write this Python command mp random rand n and then write the dimensions of the tensor. And then we get this tensor consisting of d1 times blah blah blah, dn scalar values, where each scalar value is sampled from a normal distribution with 0 mean and variance 1. So, for example, mp random rand n 5, 9 generates a 5 times 9 matrix. To take this code as a basis for sampling from an arbitrary normal distribution with mean mu and variance sigma squared, What we are doing is we say we multiply sigma times whatever we had before, a sample from a normal distribution with mean 0 and variance 1 plus mu. Here it is very important to note that in order to set the variance to sigma square, we only multiply with sigma. We don't multiply with sigma square. So multiplying the values with the standard deviation sigma creates a variance of sigma square. Now, one problem is how small should we make sigma? For example, sigma equals 0.01 seems to be a good first guess. Smaller weights result in smaller gradients, so maybe we do not want to sample too small. Another thing that we'll see is that this problem that the variance of the output depends on the number of inputs. Let's just observe that next by setting sigma to something small and see how it behaves. We'll just do some experiments. The idea is that it's easy to just try out different initializations. So we generate a desired network architecture. We initialize the weights according to the proposed algorithm, proposed initialization scheme. And then we can feed random inputs or training samples to the network and look at the distribution of the values in each layer of the network. So what we're doing next is we're actually not taking training samples. We really just sample the inputs, the inputs to the network also from a random distribution. So in the first experiment, we're going to use 10H activation, 6 linear layers, and 4096 values per layer. All right. So this is the code that can do that. What this code does is it has a weight matrix W that are the network parameters for each linear layer. And it is computed by, this is the sigma is 0.01 times, and this command here creates a normal distribution, a sample from a normal distribution that is distributed with normal 0.1, and then this changes the standard deviation to 0.01, as we discussed before. And the size of this matrix is d in, d out, and this loop generates these pairs that all of them are with this code are 496. So d in and d out is always going to be 496 and 4096 and 4096. Then we take the data. The data itself is in this vector x, and then the data is always updated, so it always stays in this vector x. So we'll feed 16 samples in the network. Each of them has 4096 dimensions by itself, and then this computes the linear layer, this x dot w, and the 10H computes the activation function. What we do then is we observe the statistics of the outputs of the first layer, the second layer, the third layer, and so on. This is the output of the first layer. The output is nicely distributed, and the standard deviation is 0.49. Then standard deviation is 0.29, standard deviation is 0.18, standard deviation is 0.11, and so on and so forth. We see the standard deviation shrinks and the distribution gets more and more peaked. And so the problem is when the output goes too much towards 0, the gradient also goes towards 0, since the gradient depends on the actual values that are propagated through the network. Also note that these histograms don't have the same y-axis scale. So the y-axis of the last layer, there is going to be a lot more values in the peak. So if we would draw it to scale, this last histogram would probably be like this tall with everything in the middle. Also, what is actually the input standard deviation? So what we sample here, the input data x, has a standard deviation of 1. It's a simple 0, 1 normal distribution. So that means that the first layer maybe cut the standard deviation in half. So it reduced the standard deviation as well as all the other layers. We can observe that the mean stays 0. This somewhat makes sense since the nonlinearity, the tanh function, goes from -1 to +1. And so we would kind of assume it keeps the values somewhat distributed around 0. Further, we can see that the values are always from -1 to +1. This is guaranteed by the tanh function since it only produces values that are between -1 and +1. However, the input, sampling from a random distribution like this, normal distribution, the inputs are not guaranteed to be between -1 and +1. Since this didn't go so well, let's just try to increase the weights. Let's increase this factor 0.01 to 0.05. So we make the factor that we see here 5 times as high. Now, that's a big disappointment. Rather than the somewhat nice bell curve shaped distributions being a bit broader and spreading out a bit more, we see that the values saturate. So the tanh function takes the input values that are generally too large and then maps them to almost like -1, or either to -1 or to 1, and only in a few cases we see output values that are somewhere in between -1 and 1. But in all the layers, starting from the first layer, we see 2 distinct peaks, one around -1 and one around +1. One aspect we do know from the tanh activation function is that the gradients in the saturated area go towards 0. So again, this poses a problem for learning. Just to give you a feeling for what some of these derivations in the papers look like, we're going through the absolute simplest, most trivial of such a version of such a derivation. We're going to use 2 facts that are true about variance, and we'll briefly review these 2 facts, so then we can use them in the derivation. The variance of the product of 2 random variables is equal to the expectation of, so the random variables are called x and y. This is expectation of x squared variance y plus expectation of y squared variance x plus variance x times variance y. Also, the variance of a scalar, a fixed scalar, times a random variable is a squared times the variance of the random variable. So we just want to kind of normalize or standardize the variance of the output to obtain a nice distribution of values. Specifically, we would like to have the variance of the input values be the same as the variance of the output values. In this way, the values will neither shrink or explode, hopefully. So we're going to do this analysis now just for a linear layer without considering an activation function. All right, so let's look at the derivation. We'll assume that xi and wi are zero mean, so that's just an assumption for this simplifying derivation. And we also assume that the expected value of this wi and expected value of the xi is 0. That means that in expectation, the weights as well as the data that is processed is 0, which means that it's just distributed around 0. The data as well as the weights are independently distributed, which means that we'll assume that if you have an image, the value of each pixel is independent of the value of the neighboring pixels, which is clearly not true. We'll just assume it for simplified model. And also the weights, we assume that they are completely independent from each other. And then also identically distributed, independently identically distributed. And then that the xi and wi are independent. So we assume that the data and the network weights are not related in any way. All right. What we're doing is we are going to look at one output value S that comes from a linear combination of input values xi weighted by the weights wi. And so we're going to sum over this value I, and we'll just have n in and subscript in input values. All right. So that's what I called d in before. Since we look at this probabilistically and we consider these to be random variables, we'll then just ask what's the variance of this output S. And this is just applying the variance. So the substitution S equals this. So the variance of S is the variance of this expression here to the right. Now, the variance of the sum of a few terms is the same as the sum of the variances of each of the terms in the sum. Therefore, we go to the next line here, equals the sum of the variances of the individual terms. Then we use this equation here. What is the variance of the product of two random variables? This is this equation that we substitute now. All right, so we have the expected value of the first random variable square times the variance of the second, and then the other way around, and finally the product of the two variances. By assumption, these expected values are 0. So we can eliminate these first two terms and just look at the third term that is left over. And now, in this sum, we sum up the same value n in times. So we obtain the final solution equals n in the variance of w and the variance of x. So first observation is that indeed, according to this simplified derivation, the variance of the output increases the more inputs are considered. That means the more terms are present in this sum. And this is intuitive from what we know about variance. So our goal is to make the variance of the inputs xi the same as the variance of the output s. That means that the variance of the weights should be 1 divided by n in. Then we would have n in times 1 divided by n in. So if the variance of w is 1 divided by n in, so these two components would cancel out, and then we would be left with the variance of s equals the variance of x, and these two terms cancel out. A property of the variance, again, is that the variance of ax is a squared variance of x. Therefore, the weights need to be scaled by the square root of 1 divided by n in. And if the weights are scaled with this factor, then we get the right thing. So we would have this square root of 1 divided by n in inside here, and then we can drag it out. We get a 1 divided by n in according to this equation here. All right. Now we could intuitively reason, and one could back that up with some form of derivation. We'll just intuitively say, well, a ReLU activation function now would kill half the values, would set half the xi's to 0, and therefore the variance should be decreased by 1/2. To compensate for this effect that the ReLU would have, we'll just add this additional scale factor of 2, or when we scale the standard deviation, or when we then we have the square root of 2 as the extra factor. So instead of scaling the random values by square root of 1 divided by n in, we now would scale by square root of 2 divided by n in. Note that this is the solution that many people derive as when they do this simplified derivation. But also notice that if we go back to the solutions proposed in the beginning of the lecture, they look a bit different than what was initially proposed. So it's more general, and they're slightly different versions. Let's try to see experimentally in this simple setup if that makes sense. So we still have a 10H activation function, but we use this scale factor 1 divided by d in square root, but so we can just divide by square root of d in, and we see on the next slide that the distribution of the values in the network looks pretty nice. Now we'll switch 10H with a ReLU. So here you see the equation of the ReLU, maximum of 0 and whatever's there. Again, we see this doesn't look so great because now, again, there are way too many weights close to 0, and the standard deviation shrinks and it gets smaller and smaller. So the values go closer and closer to 0, and that again means that the gradient also shrinks. Finally, we can use this additional 2 to correct for the behavior of the ReLU, and then looking at this is looking a lot better. Now, you say, well, maybe it's just a little broader, a few more values around 0. But the key point to look at here is that the standard deviation does not shrink nearly as fast. So we'll start at 0.83, and then it goes down to 0.81, 1 in the 6th layer, and before, by contrast, it would go down rapidly to 0.1. Finally, I would like to highlight that there are, of course, interactions with other components. Initialization depends on all other things used in the network. It will depend on regularizers. It might depend on how the network is exactly configured. And so probably a prominent interaction is the interaction with normalization. The batch normalization can normalize maybe before the nonlinear activation function to change the variance and the mean. And this definitely will interact with the initialization of the weights.